This fantastic prototype sports car is powered by a remarkable energy storage device. A device that we carry around in our pockets, and a device that's helped revolutionise the modern world, the battery. In this lecture, I'm going to investigate one of the most important scientific challenges of our generation. What's the best way to store energy? To find out, we're going to try and get into the Guinness Book of World Records with a very special battery. Welcome to my final 80th anniversary Christmas lectures. I'm Saiful Islam. I'm a professor of chemistry at the University of Bath. When we talk about energy storage, we're often talking about one thing, the battery. Try to imagine a world without them. You'd have no mobile phones, no laptops, tablet computers, or even remotes for your TV. I think batteries are amazing, but they can be very, very familiar. So I wanted to show you an unusual and slightly, in fact, I think quite scary demonstration of what batteries can do. So I've rigged this up. This is an arc welder, not something I thought I'd be doing. It uses electricity to cut through solid metal. It's one of the most energy-intensive processes you can think of. The actual tip here can reach 20,000 degrees Celsius. And that extractor fan there is going to actually take up the fumes. But the welder is hooked up to just a couple of ordinary car batteries. And come with me and I'll show you what they look like. So right here are some two ordinary car batteries, and we've hooked them up, but we've put them out here because there's a small chance they might explode. So let's try and set things up. So I'm no welder, I'm just a humble chemist, but I'll be happy to give it a go. So this is my hand in glove, and so it's really important at this stage, right, before I get down here. So if you can put your goggles on now. I tried something earlier. It wasn't a fantastic effort. Right. Let's see if that's better than my first attempt. Well, let's have a look. So if you look here, I tried to do RI twice. I don't think I'll give up my day job and become a welder. So I would say that's my abstract period, and that's my sort of dodgy period. But so anyway, I hope the sparks were flying there. So that is a very intensive process. But that, remember, that was done from the energy from a couple of car batteries. Storing energy is more important now than any time in human history. It affects all aspects of our lives. So how many of you have got phones in your pockets? I imagine most of you. So why don't you get them out? Let's have a look at them. Okay, and you can turn them on. So a simple question. How many of them are fully charged? Who's got them fully charged? Not that many. How many are less than half charged? Right. And how many of you have actually run out of battery altogether? Just a few of you. So our phones often struggle to last a single day. Over the next hour, I'm going to try and do something truly amazing. I'm going to look at how we might supercharge a mobile phone and get it to last a whole year without plugging into the mains. So I'm sure all of you, and I know I would love one of those. So how much energy would that take? So let's look at this energy meter over here. Okay, so this meter uses units we can all understand, AA batteries. Our target for the year is about 800 AA batteries, which you'll see, boom, 800. So to give you a better feel of what that looks like, I've got this large container, and I'm going to go up the ladder to pour them in. Oh, they're down there. I think I need a volunteer to help out. Any volunteers to help out? So, Judge, you want to come round? Yeah, come over. Can I take your name? Asheen. So this is Asheen, and he's going to help me put these batteries in there. So if you could pass me one bucket at a time. So this is what the 800 AA batteries look like if you wanted to power your mobile phone for a whole year. Okay, do you want to give me another bucket there? So that's 2. So this is just 2 more to go. And the last one, let's see. So you can see it's really already gone up really a high height. And then the last lot. So it's already even gone to the top. So that's what you would need to power your phone for a whole year. Can you imagine trying to carry that around in your pocket? You need some very large pockets there. Thank you. Thank you very much. Thank you very much. Thank you. So you can see already it's going to be a tough challenge. The key is storing more energy in a smaller size and a lighter weight. We want to increase something we call energy density. But first, it always helps to know our scientific history. Who made the first chemical battery? So one of the earliest batteries is right here in the vaults of the Royal Institution. And we can show it to you right now. So this is our museum curator, Charlotte, and she'll be holding it. I'm not allowed to touch it because it's very precious. Here is a voltaic pile. It was made by Alessandro Volta in Italy and given to Michael Faraday nearly 200 years ago. So what's it made of? So you can see it's got these kind of metal slabs, and they are the metal electrodes, so zinc and copper. Between them, I don't know whether you can see on the camera, there's kind of cloth, a bit of cloth there, and that would have been soaked with salt water. It might look crude, but it did store a small electrical charge. So you would probably need 1,000 of these to power your current modern mobile phone. But this was a key moment in the history of science. It was one of the first times anyone had been able to store electricity. It gave birth to a whole new field called electrochemistry. So thank you, Charlotte. Thank you. So the voltaic pile I've just shown you, and all batteries, basically work on the same principle. A good way of explaining batteries is with a very complex piece of machinery. a lemon. And here we're going to actually, something I prepared earlier. We've got basically how a lemon battery works. As before, with that voltaic pile, you've got a metal electrode, in this case a copper nail, and we've got, at the end of this one, you can see a magnesium strip, which is the other electrode. So let's have a look at this voltmeter. So if you look at the value at the moment, it should be reading 0. So if I plug this in, it should hopefully give us a voltage. So you can see that. It's gone up to 1.42 or 1.43 volts, actually 1.44. So actually it's showing a voltage. But these are the Christmas lectures. One lemon is not enough. So I wanted to go large. I told the Royal Institution I wanted to go very large. And it's so large it won't even squeeze into this lecture theatre. So follow me, and I'm going to show you what it looks like. So this here is the biggest lemon battery the world has ever seen. It's gigantic. Look at it. Over 1,000 lemons. In fact, we cut them up in half and sliced them to make 2016 lemon slices. So this is cutting-edge technology. Let me get a closer look at one of these batteries. OK, Joe, do you want to get closer to one of these batteries? So look, this is exactly one of the batteries that I showed you inside, where these are the electrodes and the clips. So let me meet the adjudicator from the Guinness Book of World Records, Craig Glenday. It's great to meet you. So let's move over to the voltmeter. So as you know, there was some issue with some of the lemons, so we weren't sure if we were going to quite reach the target. But what's the target we need to get to break a world record?
To achieve the official Guinness World Records title, you must exceed 1,000 on the meter. So we're looking for 1,000 or more to be successful. OK, so I'm going to do the connection, and it rests on whether I can connect them up properly, and we're going to pass that total. But I need a very large countdown from the audience, so I can hear it from here. So give me a countdown. 3, 2, 1. So what does it read, Craig? I'm very pleased to say it reads 1,275. So you've more than broken the Guinness World Records title. Congratulations.
Great. So, thank you. Yeah. We've done it! We've got a world record! Yay! That was exciting. It was actually very nerve-wracking. It was quite close to the edge just before this lecture. So this may be the biggest lemon battery in the world, but could it power our phone for a year? We have a scientific term for that. No way, Jose. To really understand how that lemon battery worked, we need to get at the atomic level. We need to understand the chemistry. And this, right in front of you, is a scaled-up version of that lemon battery. So let me explain what we have here. So this is the magnesium strip. That's one of the electrodes. And here we have a very oversized nail, the copper nail that was in there. And in between that is a representation of the lemon juice, the electrolyte in between those two electrodes. So that is the battery. So what's going around the side? So around here is the wire, the external circuit, where the electrons should pass through. OK? So that is basically the battery and the external circuit. So I need a volunteer, please. And I think we have one already arranged already. So Isaac, do you want to come down? So, OK. So Isaac, do you want to come round to the front here? So we've got a board for you to wear. I know it's not a very fetching board, but it tells us exactly what you are for this evening. So you are, for this evening only, you're going to be a magnesium atom. Okay? So what does a magnesium atom have? It has electrons, it does. So no, I'm glad you know. So if you stay around just to the side here, right to the side there, so you're going to hold these two electrons. So get those two hands ready. So think about these electrons, they do wander off. They're very mobile. So let's have a look. So if you hold that, we want, just to make it more difficult for you, I know you're not a juggler, you're going to hold those two electrons like that. So this is the magnesium atom with two electrons. So electrons are the smallest particles of the atom. They act as carriers of electrical charge. So when we talk about electricity, we're really talking about electrons moving. So what happens when we connect the wire? So you can see already that there's a clip there already connected to that electrode. So there's one clip here representing our other connection. So I'm going to connect that to the magnesium electrode, and I'm going to connect it to the circuit in a second. But before that, can you get ready with your electrons? So you just hold it there, but don't let it roll yet. So just hold it there, and when I connect them, just give it a little nudge, a little push around that circuit. Okay? So let me make the connection now, and then give it a little nudge there. So this electron moving is electricity, and actually would power that lamp. There you are. Give us another electron. There you are. So those electrons, i.e. this large balls representing them, are actually powering a device. And that's how the start of that process works. But there's another driving force. That magnesium atom has just lost two negatively charged electrons. So what happens there? It becomes a magnesium ion. Yes. And there is a driving force that pushes that ion across the pool, the electrolyte. So do you want to go through that pool, but very carefully, because it's got full of balls, right to the other side. So if you come to this side here. Great. So your ion now, how are you feeling? Positive? Great. So that's basically how that lemon battery worked. What happens here, there are some further chemical reactions to balance the charges. But this is not rechargeable. What happens is that once we've used up all the metal, it goes from that side to this side. And if it uses up all that metal, you actually don't produce any more electricity. So this is not a rechargeable battery, as the ones that you find in your phones. Thank you, Isaac, for helping out. And thank you very much. OK, do you want to go back to your place? Almost all of the rechargeable batteries in your phones and laptops rely on a single rare and extraordinary metal. As part of our 80th celebrations, we're inviting Christmas lecturers past to help out. To introduce you to the properties of this material, please welcome the 2012 Christmas lecturer and fellow chemist, Dr. Peter Wathers. Hi there, Peter. Hi there. Peter, I'm so glad you could join us.
Oh, it's great to be back.
So tell us a bit about your lectures back 4 years ago, 2012.
So we were looking at the chemistry of the elements, so all the different elements around us and how important they are in our everyday lives.
I really enjoyed watching them. So what was your favourite demonstration amongst the lectures?
I think my favourite one was actually when we burnt a diamond in oxygen gas. And Harry Kroto, Nobel Prize winner, came down and helped out. It was just absolutely fantastic to see this tiny little diamond in the gas there, just glowing beautifully like a little star trapped in a jar.
It is quite stunning to see, isn't it?
Right.
And remember, there are no flames coming from this. So this is just, again, the heat of the reaction as the carbon combines with the oxygen that's present flowing through here, forming carbon dioxide. Oh, that is absolutely stunning. Just look at that. It's glowing all by itself. It's absolutely brilliant.
So I've got you on for a specific reason. I've mentioned this strange material. Can you tell us a bit more about it?
Yes, so this is one of the elements, and it's a metal, and I've got a little sample in the jar here. So this metal is actually incredibly reactive, much more reactive than sort of a lump of iron will be. It's in fact so reactive that it reacts with air and with water, as we shall see in a minute. So this is, I'll just take a piece out. This is in the form of foil. And this, you can see that it's just a nice, shiny metal there. And it's the element lithium. Yeah. And this is actually, in fact, so light that it will float on water, which is rather nice.
Let's have a see, yeah.
OK, but you might want to step back a little bit.
Yes, I will do.
OK, there we go. And that's because it's instantly reacting with the water. It's the lithium metal is turning into lithium ions, which are dissolving in the water there, and also giving out hydrogen gas and forming an alkaline hydroxide solution. It's gone already.
Oh, great. Well, thank you, Peter. Tell us about this strange material, the lithium metal, and with an elegant demonstration. Let's thank Peter Wathers once again.
Thank you.
So why keep such a reactive metal in our pockets? What makes lithium so good? To illustrate this, I've got a pair of lead-acid batteries here. And how much work can they do? Well, we decided to show them a slightly different way. We've calculated how far they would turn a famous London landmark. So on this screen, you should see, this is just a time-lapse photography of the London Eye. Those lead-acid batteries could actually turn that London Eye a certain amount. So let's see how much that could be. So you can see it's only about 6%. Okay? That will be around 27 meters of those pods moving round. These are lithium-ion batteries of the same weight as our lead-acid ones there. So let's see what they would do to this London Eye. So let's have a look. They would go round 25%. So that moves the pods over 100 meters. And that's because a lithium battery stores a lot more energy than any older lead-acid battery of the same weight. It's what we call a higher energy density. And this has big implications. It's a great pleasure to welcome the 1987 Christmas lecturer and previous director of the Royal Institution, Professor Sir John Myreg Thomas. Oh, great. Hello. Thank you very much. Thank you. Your lectures were some time ago. What was the subject that you covered back then?
Crystals and lasers, and I dealt mainly with crystalline materials, crystalline platinum in particular, not crystalline lithium.
Well, related to that, I got you on for a specific reason, holding a very interesting device. Tell us about what you're holding.
Well, this is a mobile phone manufactured in Texas in 1983. It cost £4,000. It's about 5 pounds in weight. It could allow you to speak for 30 minutes, but you needed 10 hours to charge it. So I didn't buy one.
Okay.
Yeah.
So John, I think we've got some footage from a previous lecture.
It's Professor David Pye from Queen Mary College, as it then was.
Find the phone under your seat there that's ringing. Okay? Would you like to press the orange button, please? It'll take the call, and then use it as an ordinary phone. Hold it up to your ear. Hello? Can you hear me on the phone?
Very clearly.
Good. Can you tell me your name, please?
Maxwell Charles Lovell Hall.
Great. So John, it's been a real pleasure, and I'm glad you could join us to describe that particular device. So thank you very much.
It's a delight to be here.
Thank you. Lithium-ion batteries first came on the market in the early 1990s, probably way before most of you were born, actually. They have helped power a worldwide portal revolution. They've changed all our lives. So why are lithium-ion batteries so much better at storing energy? To understand that, we need to get back to chemistry, which is where I like to be. So lithium has the smallest atoms or ions of any metal in the periodic table. So this is just a lithium atom, but how does it compare to another atom in the periodic table? So I'm going to hand it over to a couple of people here. Can you just hold those? So this is sort of a relative scale. You've got lithium, and you've got the potassium. And if you could hold those, you can see quite clearly that lithium is a lot smaller. And the more ions you can pack into a battery or into a space, the more energy you can store. In fact, you can cram more lithium ions, the small lithium ions, into the same space than any other metal. So this gives lithium batteries their high energy density. Because lithium ions are so tiny, it's very difficult to see them using experiment alone. So as a chemist, I'm lucky that my research can use modern supercomputers and to model what's happening inside batteries at the atomic level. In fact, at parties, when I get invited, that is, when people ask me, what do? I sometimes say, I model. And this is a computer model of the atomic structure of a lithium battery material. So this is a lithium cobalt oxide electrode. The cobalts are in purple, the oxygens are in red, but you can see the lithium ions zipping through between the channels. So it's a very sheet-like structure, and the important stuff is happening between the sheets. So you can see the lithium ion just zipping through. So they just indicate very fast ion motion. So when you charge up your phone tonight, probably Snapchatting to late in the evening, when you see those red and green symbols, they just indicate that tiny lithium ions are moving through a battery material. Those tiny lithium ions are moving through those sheets. But as you may have seen in the news recently, batteries sometimes go wrong. They overheat, and it's usually due to short-circuiting. And I should stress that this is a very rare event, considering the billions of cells that have been sold practically every week. So we've set up a demonstration, and this one is so dangerous that we couldn't actually do it in the lecture theatre. So we're doing it outside, and we've set it up on the roof. So what you see there is a lithium battery pack. It's within a Perspex box, and right above it, you can just about see a tube. And at the top of the tube, you'll see a giant nail. And it's going to go straight down into that lithium-ion battery. And this is a serious point. Do not attempt this at home. Okay? It's going to be pulled by that small string there. That's going to release the rod, and that nail is going to go straight down. So I think we need a countdown here. All right, another countdown. 3, 2, 1. So what you're seeing there is the reaction right on that lithium-ion battery. So as you can see, that is an intense reaction just from that nail going right through that lithium-ion battery. So what's happening there? So what's happening is that the nail connects the two electrodes and short-circuits the battery, which makes it overheat. And this mimics the short-circuiting caused by bad battery design. But it's not the lithium that explodes. It's actually something else. It's the liquid electrolyte that sits between the two electrodes. And that electrolyte is made up of a lithium salt in a solvent. And that solvent is highly flammable. And get it too hot, and it simply erupts out of the casing. So we're going to see a demonstration of this right now. I think, Natasha, I think we're ready. So give us a demonstration. Great. Thank you. Okay, so that's a very violent reaction. So this overheating is sometimes called thermal runaway, which is a very rare event. Obviously, as long as you don't drive a nail through your battery or phone. So let's get back to our original question. Can we power our phone for a whole year without plugging into the mains? Well, we've been working very hard behind the scenes. And guess what? We've done it. Here it is. We've done the maths, and this would definitely run your phone for a whole year. Inside, as you can see, are several lithium-ion batteries, the size of car batteries, wired together. I need a volunteer here. Yes? Actually, front row, yeah, come on over. So this is on a sort of a rucksack. Oh yes, can I take your name?
Adam.
Adam, sorry. Adam, well Adam, you're going to try and lift that up. So why don't you come round and give it a good pull up. You're probably stronger than I am. So can you try and lift that up?
Yes.
Yeah. That is heavy, isn't it? Would you like to carry that with your mobile phone? No. Right, well you're giving that a good attempt. So come over here on this side here. In fact, do you know how much that weighs? You probably could tell. That weighs 30 kilos. And actually, I can barely lift it as well. So you're not going to put that very soon into your pocket, unless you've got very large pockets. So to make this work, we need somebody else to help out. Please welcome Britain's strongest woman, Andrea Thompson. Thank you. Thank you, Andrea, for joining us.
Thanks for having me.
You are Britain's strongest woman. What did you have to do to get that accolade?
What I had to pick up 220 kilos in my hands, pull a truck, a 3-ton truck, and lift a series of Atlas stones from 80 to 120 kilos.
A 3-ton truck?
Yeah.
So how far did you move that?
20 metres.
20 metres?
Yeah, it was tough.
All right. Well, let's see what we can do with this. As you can see, we've got some straps here. So I wonder if you could pick that up and see if you can put that on your back.
Okay.
Let's give it a go. So that's 30 kilos, remember. It's a bit of a tight strap. There you are.
Thank you.
Does that fit now?
That's fine.
Oh, yes. That looks quite snug. Yeah, give it a clap. Obviously, that might be a solution for Andrea, but I don't think it's going to be practical for everyone else. So you can see it's a possible solution, but not quite a practical one. You're going to carry that around for a whole year next to your phone. Let's thank Adam once again, and we're going to thank Andrea. Thank you. Can you do us a favour? Can you take that off with you? Thank you. Thank you. So can we do better? Can we help our phones last longer on a single charge? So we've talked about more powerful batteries, but obviously if your phone uses less, then obviously it will last longer. So which function on your phone uses the most energy? Well, to answer this question, we need to smash open someone's smartphone. Actually, at this point, I'd love to use my daughter's, but I couldn't possibly do that. So any volunteers to have their phones smashed? Yes, give us your phone. Okay, right, let's put it there. So, right, we need a countdown for this. Okay, so 3, 2, 1. No, no, no. No, of course I couldn't do that. Don't worry, we've got our own set up here. So this is obviously something, again, we prepared earlier. It's got a voltmeter there and a typical mobile phone. Mobile phones do lots of things, okay? And this just actually gives an indication of the energy used by the different functions within that mobile phone. And the numbers are really a relative number. So don't worry about the units exactly, but just look at the relative values. So at the moment, you can see the relative values are fairly low, okay, and that's the phone is on idle. So now, I think we're just turning it on, and you can see straight away, just by turning it on, the energy usage has gone up. So if you look at the photo function, it whacks up. Look at that. Taking photos, you can see really the energy usage sometimes touches numbers as high as 400. And then you've got to use the internet to transmit that. So this is the Wi-Fi. So Wi-Fi drops down a bit, but still you've got relative energy usage. And then lastly, I think we're going to go on to Twitter. We're going to go to the RI website, and I think you'll see a very dodgy photo. There you are. So again, you can see the different functions are using different relative amounts of energy. So taking photos and having your screen lit up uses your battery up quickly. But if you really want to save battery life, then GPS is worth turning off too. Saving battery life is okay, but can only get you so far. To stand a chance of powering our phone for a year, we're going to need a new battery design. So hundreds of research labs around the world, including our research lab, are searching for the next big battery discovery. There are lots of new designs out there. And I'd like to tell you about one of the most exciting examples, actually theoretically the best battery. Can you please welcome Dr. Lee Johnson from Peter Bruce's group to operate this battery for me. Thank you. So this unusual battery uses just lithium metal reacting with oxygen from the air. So it's a lithium oxygen battery. This makes it very lightweight and very energy dense. So what you have here, this is a vacuum chamber, and inside it is actually the lithium battery cell. It's not powering these lights at the moment, okay? The battery itself is made up of what we call a chemical sandwich. Okay, so let me show you what that sandwich looks like. Here it is. This is about 0.5 gram of lithium metal. Okay? And that's within that very cell. Only 0.5 gram of lithium metal. The other part of that sandwich is just this kind of carbon mesh. And this carbon mesh has a very high surface area. And what that allows is that the oxygen to react with the metal. So if you let the air in, we should see, hopefully, the lights go on from that reaction. So
you ready?
Tell us what you're going to be doing here.
Okay, so there's a vacuum in here, and I'm going to open this valve, and that's going to let the air into this chamber, and hopefully what you'll see is, you see the pressure go up here, and you'll see these lights come on. So are we ready?
Okay.
Yeah? Okay. So you'll hear a hiss. And we should see it start to light up now. Okay.
So there, see, you can see it going. So this is being produced by this lithium oxygen battery. And that was only 0.5 gram of lithium. So this stores a high amount of chemical energy, at least 3 times more energy than today's lithium-ion batteries in your mobile phones. So these batteries are exciting. They do need more research, but they're probably at least a decade away for practical devices in your phone. So let's thank Dr. Lee Johnson again. Thank you. So far in this lecture, we've mostly been looking into how to power our phone for a year. I'm going to move away from that for a moment because I want to talk about some other ways energy storage affects our lives. One important area is the huge growth in renewable energy, such as wind and solar. Last year, the UK generated a quarter of electricity from renewables, solar, wind, and wave power. But what happens when the wind isn't blowing and the sun isn't shining? So currently, there's no single solution. Batteries will play a part, but we need something on a much bigger scale. There are a number of options. People have tried pumping water up into raised reservoirs when energy is plentiful and releasing it to give us power at a later date. This is sometimes called pumped hydro. But there's one fascinating form of large-scale energy storage I'd like to tell you about. It's called magnetic energy storage. This is a strip of powerful magnets. So you can see here, it forms a track round here. And what we have here is some superconductors in that liquid nitrogen. These superconductors actually only work at very low temperatures. So could you place that on this powerful strip of magnets? And let's see it levitating around. So let's give it another nudge there. Yes, it goes. Yes. Yes, that's much better. There it goes. Oh! Yes! Yes. A superconductor is a material that shows powerful magnetic behavior. The reason this vehicle floats is because inside the superconductor is an electric current that meets no resistance. And if you make a ring out of this superconductor, it forms a never-ending electrical circuit. So this circuit can store large amounts of electricity to be used later on. Okay, so have an applause there. There's one other crucial area of our lives that better energy storage could completely revolutionize: the cars we drive. We saw that sporty electric car at the beginning of the lecture. Thanks to advances in lithium batteries, we're at the dawn of the era of the electric car. But they've got stiff competition. We've seen that a couple of large lithium batteries could power the London Eye a quarter turn. So what would the same weight of petrol do? So that's a quarter of turn for the lithium-ion battery. How far would that petrol go? So let's have a look. It'll go 3 revolutions, 4, 16, 18, 19, 20. 20 revolutions of the London Eye. It stores more than 50 times the best lithium-ion battery. So in terms of energy, it's way, way ahead. But as I'm sure you'll know, petrol has some serious problems. So a bit of chemistry here, and I am a chemist. So petrol is made up of long chains of hydrogen and carbon, which we call hydrocarbons. So these are beautiful molecular models of, this is octane. So you can see the black are carbons, The small white balls are hydrogen, but there is a problem. When you burn these, you get pure carbon, that black, but you also get something else, something you can't see, carbon dioxide, and that's this feature there. So that's carbon dioxide, so if you take that. So this is carbon dioxide. So the carbon has reacted with oxygen, so the reds are the oxygens, and the carbon is in black. But that's just the molecular model. We're going to see how much energy they produce, but also some of the pollution they may produce. So we're going to burn just a bit of petrol. There's a bit of petrol in that crucible, and we're going to see the effect of burning that. Okay, so there's some petrol burning, and what happens when you just put a simple tile over it? Obviously, do not do this at home, and you can see very quickly how much carbon soot's being produced. Okay. Thanks, Natasha. So that's the problem with today's cars. Petrol-powered road transport produces a lot of air pollution, and going electric will be much better for air quality and better for the planet. But first we need to solve a big issue with electric cars. Can we go a long distance without charging? Some people call this range anxiety. Did you know, though, that most car journeys in the UK are less than 30 miles? But obviously it's nice to know that we can go further if we need to. And I've always wanted to celebrate New Year in Scotland. So I wanted to find out if I could drive an electric car from the Royal Institution here to Edinburgh on one charge. So what you can see here, hopefully you can, if you're not geographically challenged, that here's London, and to get to Edinburgh, you'd follow the A1 right up this path here. So we want to look at different types of electric vehicle and see how far we could go. So I need a volunteer to help with this. So I should get somebody from there. Do you want to come down? Great. Okay, so can I take your name? Sam. Sam, could you come on this side here? So we've got some different vehicles, and I'm going to pass them to you. Right. So first of all, we've got an electric golf cart. Okay, so what I'd like you to do, you're going to start there. If you could just gently go up the A1, and when you feel a bit of magnetic pull, just stop there. Okay, let's go along there. Yes. So the second vehicle, the G-Whiz. Right, that's a G-Whiz vehicle. That's an electric vehicle. Right. See if you can actually feel some magnetic tension again. There, does it feel there? Yep, that's it. Actually, it doesn't go much further. That G-Whiz car goes only about 50 miles outside London. So let's go to the third vehicle. And this is a Nissan Leaf. This is an all-electric Nissan Leaf. So if you can go along the A1, about there. So that's actually about 124 miles outside London. Okay, so there are some actual London buses that are electric powered. Okay, let's have a go. Let's do up from there. Let's see how far you can get. Is it feeling it there? Around there. That's a good one. So that is about 180 miles, just a bit further than Nissan Leaf. The last one, this is the latest Tesla Model S. Okay, and let's see how far that can go. So you can start from the London bus. So let's see. Just gently go up there, about there. Doesn't quite get to Edinburgh. In fact, it's gone about just over 300 miles from London. So thank you again. Thank you. Thank you. So as you've seen, I'm not going to get to Edinburgh on one charge. Petrol cars still have the edge on range. But batteries are improving thanks to worldwide research efforts. So one way electric cars are seriously competing is in performance. And if you love fast cars, like that sporty electric car I arrived in, going electric might not be as bad as you think. I asked the 2014 Christmas lecturer, Professor Danielle George, to put this to the test.
Hi Saiful, hi everyone. I'm here at a closed-off racetrack with two very exciting cars. One of them is a petrol-powered supercar, the Bentley Continental Titan, which has been souped up to within an inch of its life. The other is an electric car, the Tesla Model S, which looks a bit like a posh saloon. But I'm going to be putting these two cars to the test to see which one reaches 60 miles an hour the quickest. It's very, very exciting.
Three, 2, 1.
Wow! Oh my word! Good grief! That is amazing! Oh, I'm still shaking. It is seriously like being on some sort of roller coaster. It is so fast and so quiet.
And I definitely left the Bentley Continental for dust.
Now, an all-electric car similar to this actually holds the record for the fastest 0 to 60 time. And there's a reason for that. A petrol car uses gears. And so as we increase our speed, we need to increase the gear that we're using. And you can really see this on this graph here. So what we have are both cars plotted here, time and speed. The red is the electric car and the black is the petrol car. And you can see the speed and then the gear change here and then the increase in speed again after the gear has changed. But with an all-electric car, we get peak performance from that electric motor as soon as our foot hits that pedal. So there's no need for gears. And the result is one mean, green speed machine. And this is all possible thanks to better batteries.
Yes. Thank you, Danielle. I think we'll be seeing a lot more electric cars on our roads in the future, but maybe not going as fast as that one, obviously. For the moment, we're still stuck on petrol. Is there anything that can beat it in terms of energy density? Here are our lithium and potassium atoms from earlier. And this is, I think, it's nice to use a couple of volunteers. So if you hold on to those. So I showed you, just to remind you, that's potassium and that's lithium. And just to show their relative sizes. Obviously, that's not the real size of their atoms. But there's an even smaller atom we can use. Hydrogen, just a single proton. So I might as well put it right there. So if you just hold that. So you can see there's relative sizes. And this is to scale. Hydrogen is 5 times smaller than lithium. In fact, hydrogen is the smallest and lightest element in the periodic table. By weight, hydrogen is the most energy-dense fuel. I think it's London Eye time again to see how they compare. So if you remember, 30 kilograms of lithium battery turned it a quarter. Okay? The same weight of petrol turned it 20 times. This is the same weight of hydrogen fuel as a liquid. Let's have a look. Starts off 20, past 30, past 40, 62 revolutions. It would power it for 3 whole days. There's no doubt hydrogen contains a huge amount of energy. And I can show you this with another simple demonstration. A balloon full of hydrogen. But this demo needs hands over your ears. Okay. Oh, yes, yes. Right, so can we harness the energy from this powerful chemical reaction more efficiently? Yes, we can. Hydrogen is used in things called fuel cells. They're actually being used to power several London buses right now. So can I use this superfuel to power my phone? Okay, this is a commercial fuel cell. It's a tiny one, but you can't quite see inside it. So we've got a demonstration fuel cell to show how it works in this Perspex device here. So what we have here is the oxygen and the hydrogen. If they react within this fuel cell, they can produce energy, and that can be shown easily by this fan here. There you are. There. A fuel cell is very similar to a battery. It has two electrodes and electrolyte, but there's a big, big difference. The battery is self-contained. A fuel cell needs to be fed with hydrogen as a fuel. So let me drink a typical fuel cell byproduct. It's just water. So you can't get any cleaner than that. But can it power my phone? Shall we plug our phone into our working fuel cell? Okay, so this is a typical phone. So let's turn on the device. Hopefully you can now see the charging. So this could power our phone for a whole year without plugging into the mains, but we still need to top it up with hydrogen. Sadly, hydrogen is not the answer to all our energy problems. Not yet. We have to store it at a temperature of minus 250 degrees Celsius to keep it a liquid. This means the hydrogen is costly to store, takes a lot of energy to produce, and has safety issues. Finding better ways to store energy is still a vital challenge. In these lectures, we've celebrated the 80th anniversary with Christmas lecturers past. We've celebrated energy in all its different forms and broken a world record. I've got one final energetic celebration. I want to go out with a big bang. Hands over your ears and goggles on. We're at the dawn of a new era in clean energy. The next chapter of Fueling the Future is for all of you to write. So go out and charge ahead. Thank you and good night.